Hello, ladies and gentlemen. Welcome to the New York City Category Theory Seminar, the last of the talks in, spring 2026. And today we have George Helfer talking about set-theoretic universes and paradoxes in elementary totality. Take it away. And he's going to tell us four things about them. Ready? Go.
Okay, thank you very much for letting me speak here and for organizing this very nice seminar. My name is George Helfer. George is short for Joseph. I'm from Montreal, Canada. And I did my undergraduate degree in Berlin at the Technical University of Berlin. I did a master's degree in Montreal at McGill University, and then a PhD at Stanford. And then I did a postdoc at in LA at the University of Southern California. And now I'm here in New York at the Simon Center for Geometry and Physics at Stony Brook University. And I'm going to tell you about two topoi and about universes, and maybe if we have time about paradoxes.
So just do the okay on top.
Oh.
And if there's a way to get rid of me, if I don't know how big your slides are, that doesn't serve any purpose. Okay, perfect.
Okay, so I'll begin with an overview of what we're talking about. So there's two goals. One is to describe a foundational theory for mathematics based on the two category of categories. And the other is to explain how to construct models of set theory using this framework. And I'm not going to assume everyone is familiar with all the stuff that goes into this. So I'll be trying to provide a little bit of background on these topics, on topos theory, on two categories, and on models of set theory. And I'll be providing the foreground. The things on top of the background will be two topos theory. That's something which is rather new, something I'm developing, so not something I invented. And the general business about what it means to sort of find models of set theory in this categorical setting. So yeah, I'll try to do it. I'll try to do my best to provide this background, but certainly I may assume things or say things that you're not familiar with. So please, I encourage you to interrupt me as much as you want and ask for explanations or clarifications. And in general, any questions you have, I'll be happy to address if you interrupt me. Though I reserve the right to move the discussion to the questions period at the end, which I'll try to leave some time for. Okay, so I'll begin with some background on topos theory. So what's the definition of a topos? It's a certain, and here, there's a couple of different notions of topos. I'm always talking about the one which is called an elementary topos. So that's always what I mean by topos. It's a category C with certain properties. Has finite limits, which by one of the fundamental theorems of category theory is the same thing as having a terminal object and having pullbacks. It has exponential objects, also known as internal Homs, and it has a sub-object classifier, omega. Alternatively, equivalent axiomatization is that, finite limits again, and power objects. So right now I'm going to say a bit about what sub-object classifier is and what power objects are. If you don't already know, I'm not going to go over what exponential objects are, but they're also not going to play a big role in the talk. But intuitively, it's the object of maths from X to Y. The most important example of a topos, the example which the whole theory is sort of axiomatizing or trying to generalize, is the mother of all categories, category of sets. So that's an example of an elementary topos. So what is the sub-object classifier? Like all things in category theory, it's defined by a universal property, or in other words, it represents a certain functor, namely the sub-object functor. So I have my category C, an object A. The Homs from A to omega are in bijection with the sub-objects of A. So I remind you, a sub-object is just a monomorphism going into A, taken up to isomorphism. So if I have two different monomorphisms into A, which are isomorphic to each other, making the triangle commute, I consider them equal sub-objects. And the point, of course, is in set, two sub-objects are isomorphic if and only if they have the same image in A, and therefore the set of sub-objects in the categorical sense is identified with the set of subsets of the given set. So what is the sub-object classifier? So all topos theoretic notions should be referred back to the motivating example of the category of sets. In that case, the sub-object classifier is just the set 0, 1. And how do we see this isomorphism in that case? Well, a map from a set A into the set 0, 1 corresponds to the subset of which it is the characteristic function. So in other words, the subset is the preimage of 1 under that. So it's very well known that we have such a bijection in that case. Omega is also known as the object of truth values. So in ordinary mathematics, that is to say in the category of sets, there are just two truth values, true and false. So that checks out. And you can think of a map from A to omega as asking which elements are in the given subset, or it's the proposition a given element is in this subset, and the answer is 1 true or 0 false. Now, in a general topos, omega can have more truth values. So there can be more than just true and false, which is one of the many things that makes topos theory interesting. But there are always at least the two main truth values. So there are always the two elements. By an element of an object in a category, we always mean a morphism from the terminal object to that object. And there are always two special elements of omega called true and false. Now, to understand what these elements are, we have to understand what what the sub-objects that they classify are. So an element from 1 into omega should classify a sub-object of 1. Now in set, 1 is the terminal object is the one element set. It has exactly two subsets. The whole thing, that's the identity map, and the empty set, that's the map from the initial object. And those correspond to the two truth values. In a general topos, there may be more truth values, which is to say there may be more sub-objects of 1, but there are always at least these two sub-objects, the whole thing and the minimal one, the map from the terminal object, and so we always get true and false. Okay, next, power objects. So power objects are also given by universal property, which is a little bit more complicated, but still not too bad. The power object Px represents the families of sub-objects of X functor. What do I mean by this? So, intuitively speaking, it's clear that a map from a set A to the power set of X should be a family of subsets of X indexed by A. So that's what's meant by this thing. Sub XA is the set of A-indexed families of subsets of X. How do we define that formally? It's simply a subset of the product A times X. So I claim that a subobject of the product should be thought of as an A-indexed family of subsets of X. And it corresponds to this picture. So here's the product A times X. And here's this subobject P in it. And then for each element of A, I can look at this slice. This slice is isomorphic to X. And when I intersect it with P, I get a subset of X. Therefore, for each element of A, I get a subset of X. That's an A-indexed family of elements of X. So that's why this identification makes sense. So that's the universal property of the power set. Again, what is it in set? Obviously, it's just the actual power set, right? And the actual power set in set does satisfy this universal property. So the power set is related to omega in the following way. First of all, omega is isomorphic to the power set of the terminal object. So that makes sense according to our previous discussion. The elements of omega should correspond to the subsets of 1. So that checks out. Conversely, the power set of X is the internal Hom, the object of maps from X into omega. Which also makes sense because the whole point of omega is that objects from X into it were supposed to be subsets of X. And the power set of X is supposed to be subsets of X. So anyway, this is certainly plausible. And it's something you can prove. And when you're proving that the two definitions I gave of topos are equivalent, namely the one using power objects and the one using the subobject classifier, you of course have to use this. This is how you do it. This is how you interdefine these two notions. Okay, an additional assumption that we often make about topoi, so it's not in the definition I gave, but often when one says elementary topos, it's assumed that it also has a natural number object. So I'll remind you what that means. natural numbers object, like everything else, is defined by a universal property. And it's a strikingly simple one. So it's equipped with an element called 0 and an endofunctor called successor, and it's universal with respect to this property. So given any other object A, an element of A and maybe I said endofunctor here, but I meant endomorphism. And an endomorphism of A, there's a unique map from N to A making this diagram commute. And we have to contemplate why this is true in the motivating case when C is the category of sets and N is the actual set of natural numbers. And it's simply the principle of recursion or iteration. So in that case, given A and F, this map capital F is defined by sending by sending N, the natural number, to the nth iterative of F applied to A. Okay, the details needn't worry you too much, but it's very easy to see that the actual natural numbers do have this property. And as with all universal properties, this determines N up to isomorphism. So that's usually also somewhat floating around when we're talking about elementary topoi, that we're assuming there's a natural number.
Or another way of phrasing it is that is your diagram you drew is a translation of Peano axioms into category language.
Well, yeah, that's a great comment. I would say that it's rather a theorem of pride that this condition of being a natural numbers object is equivalent to the Peano axioms. I would say this is slightly different. Peano axioms include the axiom of induction, whereas this is a simple version of the axiom of recursion. But Fried famously proved them to be equivalent.
Yeah.
Thanks for the comment.
Sure, that's right. It wasn't a perfectly exact translation, as you point out.
Right.
Yeah.
And thanks also for setting the example of interrupting me. I encourage everyone to follow his lead.
There are those who say that the category of finite sets is also a topos, so they don't require a natural number object.
Very good. Yeah, I was about to say that. So examples of topoi. So first, the category of set I said is the main example. And as Noson just said, the category of finite sets is also an example according to the axioms I gave, but it doesn't have a natural number. So the natural numbers object is what sets a general topos apart from this kind of finite one. Okay, and then the other examples are more complicated. Given any small category C, you can form the category of pre-sheaves, which just means the set value functors. And that is famously also a topos. And more generally, given any site, in the sense of Grothendieck, a category of the Grothendieck topology, then the category of sheaves is also an elementary topos. I'm not going to have any time to get into the very beautiful theory of the categories of pre-sheaves and sheaves. But I should say that they're really important for giving the flavor and substance to topos theory. As with any abstract concept, the sort of meaning of the concept comes through on the basis of the particular example that it abstracts from. And in the case of topos theory, it's really these particular categories is where it all started. Okay, so the axioms for topoi are very simple and very few in number, but their consequences are very great. So the things that you can derive on the basis of the topos axioms are very strikingly vast, and it's very pleasing to do to derive everything starting from the axioms, but I'm not going to do any of that. I'm going to just sort of jump to the conclusion, which is the logical structure of a topos. So I'm going to try to tell you about something about that by means of some examples. So let's fix a topos C, an object, a morphism, an endomorphism of the object, and a binary relation on it, by which I just mean a sub-object of the product of it with itself. And we consider this logical formula. X is less than f of x. So set theoretically in the category of sets, I have a set with a function on it and a binary relation, and this is the predicate which says of an element x that it's less than its image under f. And set theoretically, I could now form the subset of x consisting of all elements satisfying this predicate. And the point I'm making now is that you can also do this in any topos. So I claim that we can define some kind of subobject of X, which it's reasonable to use this notation for, the usual set constructor notation. And now I have to describe what is the subobject. So the subobject is defined in terms of how it behaves with respect to generalized elements of X. So before I said an element of an object in a category is a map from the morphism from the terminal object. By a generalized element, we mean a morphism from an arbitrary object U. And what we should have is, just like for the set A, I would like to say that an element at little x is an element of A if and only if it satisfies the formula phi. I would want to say that here too. That given a generalized element of capital X, it is an element of this subobject if and only if it satisfies this predicate. So what do I mean by these two things? Well, given this generalized element of X, to be an element of the subobject simply means that it factors through this monomorphism. That's simple enough. What is f of x? Well, that's also simple. Given a generalized element u to x and a function from x to x, f applied to x is just a composite. F composed with x. And now I can look at this map into the product consisting of x on the first coordinate and f of x on the second coordinate. And to say that that satisfies this relation is simply to say that it factors through this monomorphism. And so that's what characterizes the subobject, that a given element x factors through it if and only if this map factors through the subobject. And it's a general fact, which is easily seen, that for any subobject in a category, it is determined by which generalized elements factor through it. Just like an ordinary subset is determined by which elements belong to it. So this completely characterizes the subobject. Any questions about that example? Okay, and then similarly, of course, there's nothing special about this formula. We can do it with any formula phi of x in place of this particular one. Now, what the any here is in quotes because, I mean, as always, when it comes to formal logic, you have to say exactly what you mean. You have to describe the class of formulas you're talking about. But there's a very reasonable, naturally defined class of formulas such that you can always make sense of this subobject. So that's the first aspect of the logical structure inside of topoi. Oh, one more comment about this is, this was a particularly simple formula, of course. To interpret general formulas, you have to deal with the different logical connectives, with quantifiers. And so you can do all of that. It's a little bit complicated, but that's the power of the axioms of the elementary topos, that they allow you to interpret all those things. Okay, next example is, in this example, we had a predicate with a single free variable x. Next, we consider a sentence or closed formula, which doesn't have any free variables. And in that case, we're not going to get a subobject, but a truth value. Okay, so we fix the same setup: object, endomorphism, and a binary relation. And now we consider this closed formula. For all x, y, x is less than y implies f of x less than f of y. So again, set-theoretically, this is a binary relation, so something like a partial order. And this is, of course, just saying that f is monotone with respect to that relation. Okay, so now the interpretation of this in a topos is now going to be a truth value. So I'm writing square brackets phi for the interpretation of phi, and that's going to be a truth value in the topos, an element of omega. Or equivalently, a subobject of one, because those are in bijection with one another. And I'm not going to exactly tell you what element this is. I'm only going to tell you under what conditions this truth value is equal to true. So we always have this special element of omega called true in any topos. And I'm going to say, what is the condition for the interpretation of the sentence to be true? And the answer is, it's again something about all generalized elements. So when we see for all x, y here, we should interpret that as for all generalized elements x and y. And then it should say x less than y implies fx less than fy. And we already know how to interpret both of those. X less than y means that this map into the product factors through the relation. Fx less than fy means that these two composites, x composed with f and y composed with f, factor through this. Okay, so the truth, this interpretation of phi being equal to true says that for any x, y satisfying this, they also satisfy this. Okay, and again, for general sentences, it's going to be quite a bit more complicated, but you can always do it. There's always a way to extract a truth value in the topos from an arbitrary sentence of an appropriate kind. Okay, so
Excuse
now
me.
let's talk about.
Just a question, but you also fix morphism, right? So it's all relative to particular morphism F, right?
Yeah, that's a very good point. I mean,
Yeah.
there's two ways of saying it. One is that there's something called the internal language of the topos. So we have all these things in the topos. We have the objects, the morphisms in the topos, and all these relations in the topos, which are sub-objects of products. And on the basis of those things, we can create a language where the sort of basic symbols in the language come from the elements of the topos. So the sorts in the language, which the variables can range over, are the objects. The function symbols in the language come from the morphisms, and the relation symbols in the language come from the relations. And then on the basis of that, whenever I have a formula written in that internal language of the topos, it has a truth value. The other interpretation is I start with a formal language. So these are just meaningless formal symbols, and then I interpret them in the topos. So I start with just a bare sentence, and for each of the function or relation symbols and each of the sorts, I choose corresponding elements in the topos. And then with respect to that interpretation, I get the truth value. So yeah, one way or another, before getting the truth value, you have to say how the parts, the basic symbols of the language correspond to morphisms and relations in the topos. Further questions about that? Thank you for your question.
Yeah, thank you.
Okay, so now let's look at some examples of sentences I might be interested in interpreting in a topos. The fundamental theorem of arithmetic. Every natural number can be uniquely written as a product of primes. So this is some logical sentence. It's a sentence about natural numbers with its multiplicative structure, and it's something I can express in the topos if I have a natural numbers object. So I can write that down as a formal sentence and then ask whether it's true in a given topos. The continuum hypothesis. Every infinite subset of the real numbers is either countable or infinite, or sorry, has a cardinality of R. That's also something I can interpret in a topos. So this involves further aspects of topoi, which I haven't gotten into, namely that you can always define the object of real numbers. The way you do that is in the usual way that we setting off from the natural numbers, usually construct the real numbers using products and power sets and so on. These are constructions we have available in any topos, and therefore in any topos we can construct the real numbers, and therefore it makes sense to ask whether the continuum hypothesis holds in the topo. Similarly, the axiom of choice. You can also ask about that. Here are a couple of other stranger examples. Here's a sentence. Every function from the closed interval to R is continuous. So here again, I have to translate this into some sentence written in formal logic in order to make sense of interpreting in a topos, but then I can. And the interesting thing about this sentence is it's obviously false. We all know that there are many functions from 0, 1 to R which are not continuous. You can insert any kind of discontinuities you want. Nonetheless, this sentence goes by the strange name Brouwer's theorem. I'll say something about why in a moment. Here's another false sentence. Every function from the naturals to naturals is computable. That's also false, for example, because there are only countably many computable functions, but uncountably many functions from the naturals to the naturals. This statement is a kind of perverse version of the Church-Turing thesis, which says that every intuitively computable function is computable in the formal sense, Turing computable. This is literally just saying every function whatsoever is computable, which is obviously false. Now, what do I want to say about these sentences? The sentence 1 holds in every topos C. Every topos satisfies the fundamental theorem of arithmetic. Why? This is because of another thing about topoi which I haven't told you yet, which is that not only can you carry out all the standard set-theoretic constructions in topoi, but they also satisfy all the standard set-theoretic axioms. So all the usual ways that you would expect sets and functions and relations to behave, they all behave that way in a topos. Therefore, anything that you can prove on the basis of the usual set-theoretic axioms, which is to say the usual axioms of mathematics, has to hold in any topos. So because I can derive the fundamental theorem of arithmetic from the basic axioms of set theory, therefore it has to hold in every topos.
Right, but it might want to mention that topos, you have an intuitionistic logic, so only things that can be proved
Thank you. I'll mention
intuitionistically.
that in a moment.
And 4. Yeah, go on.
Which is what's going to get you off the hook with everything else.
Yeah. Thank you. Yeah. Absolutely right. In the case 2 and 3, these are statements which are famously independent from the usual axioms of set theory. And correspondingly, there are some topoi where these sentences hold and others where they fail. So it's only really the basic standard axioms of set theory that have to hold in every topos, not these contentious undecidable statements. And in fact, the fact that there are such topoi where they hold and where they fail, which is it's non-trivial to construct such things, this really gives you a proof of the independence of these statements.
You chose the fundamental theorem of arithmetic, but you could have chosen a lot of other things.
I just tried to take a very basic sentence that everyone knows.
Fermat's little theorem or something.
For example, yeah, any standard theorem of
okay.
mathematics, although one has to be careful for the reason someone was just pointing out. Namely, 4 and 5 are both statements which are false on the basis of the usual axioms of set theory, right? The negations of these statements are provable on the basis of the usual axioms of set theory. There exists a function which is not continuous. That's provable. There exists a function which is not computable. Yet, 4 and 5 are also such that there exists topoi, some topoi where they hold and some where they don't. And the catch is exactly the one that was mentioned. And it's a very interesting thing that I'm not going to have time to get into, which is that the set-theoretic principles that hold in general in a topos aren't the axioms of classical set theory, but of intuitionistic set theory. So the internal logic of a topos is always intuitionistic, which if you're not familiar with it, I'm not going to go into what that means, but you could ask me about it maybe in the question and discussion period. And it's simply the case that though these sentences are both provable on the basis of classical set theory, they are not provable and they're independent from the axioms of intuitionistic set theory. And indeed, the fact that they're independent is witnessed by the existence of these models, of these topoi, where they either hold or don't hold.
So one thing I'd be pointing out, even without going into it, is that the point is that intuitionistic logic is weaker than Boolean logic. So every statement provable in intuitional logic can prove in classical Boolean logic, but not the other way around.
Yeah, thanks. Yeah, that's a great point, and I'll just repeat it. Yeah, so the intuitionistic logic, the one that holds in a general topos, is weaker than classical logic. So, yeah, so any sentence that you can prove it. Okay, so this gives you a good idea of the kind of a little bit of a feel for the internal logic of topoi, and also for the richness of the subject. That each topos really gives you this whole world of mathematics where most things work as usual, but then there can be interesting variation.
I don't think you can state the Church-Turing thesis in an arbitrary topos. It has to be an effective topos or a...
No. Well, okay.
Realizable,
at least
realizable topos.
I mean, my understanding of this is that the effective topos gives you an example where this is true, but the statement itself you can state in general. So you
still define a Turing machine.
Exactly. You say internally what you mean by a Turing machine, and then you quantify over functions from end to end. You say for every function there exists a Turing machine such that the values of the function are determined by the Turing machine. And I mean, from my point of view, that's what makes the effective topos interesting. That it's something you can state in general, so you can ask the question, is every function computable? And then you say, in this topos, it is true. If it was only something that we could state with respect to that topos, it wouldn't have the same force. Thanks for the comment. Okay, so now I want to talk about the role of topos theory as a foundational theory for mathematics. So, when I say foundational theory, I mean, what do you mean by foundational theory? I mean some axiomatic theory from which you can define all the usual objects of mathematics and prove all the usual theorems about them. So, an axiomatic theory in general is given by some undefined or primitive notions and then some axioms. So the example, of course, of an axiomatic system is Euclid's, in which there are 3 primitive notions: point, line, and incidence. A point lying on the line. And then there are such axioms as given any 2 points, there exists a unique line to which they're both incident. In the standard axiomatic set theory, there are just 2 primitive notions, set and the membership relation, one thing being an element of another. And then the axioms are the usual axioms, say, of ZF, extensionality, power set axiom, union axiom, and so on. Topos theory, regarded as a foundational theory, is just a little twist on set theory. Instead of making the basic notions set and membership, you make the basic notions be set, function, and composition of functions. So this, even if I knew nothing about category theory or topos theory, and I was just trying to axiomatize set theory, this is a very natural way I might try to proceed. And we know exactly what the axioms of this foundational theory are. They're, first of all, the category axioms, associativity and identities for functions, and then the topos axioms, which I told you. Finite limits, which is to say terminal objects and fullbacks, power objects, and then probably we also want to throw in natural numbers object. That's like the axiom of infinity in set theory. So these can be viewed as 2 alternative types of set theory, 2 foundational theories, and the relationship between them is well studied and something which is also part of this project I'm telling you about, and I'll return to it later. Okay, so that was it for the crash course in topos theory. Any questions about that before I dive into the next thing? Okay, so now I want to tell you something about 2 topos theory. To start with, what's the basic idea of topos theory? 2 topos theory. It's that, okay, I hope everyone is familiar with this kind of notation. This is to this as this is to this analogy. So topos is to the category of sets, as 2 topos is to the 2 category of categories. So just as the topos theory is an attempt to axiomatize the basic properties of the category of sets, 2 topos theory is an attempt to axiomatize the basic property of the 2 category of categories.
Is Rush Street had the notion of a cosmos? Is this the same thing?
Very much in the same spirit, yeah. So first, let me just give a little refresher about what I mean by the 2 category of categories and by 2 categories in general. So the best way to access the notion of 2 category, or I think the easiest way, is through the general notion of enriched category, which I'll recall. So the basic idea of enriched category is that I start with an ordinary category between any 2 objects that have a set of morphisms, but instead of talking about a set of morphisms, maybe I have an abelian group of morphisms, or a topological space of morphisms, or in general, an object of some arbitrary category V of morphisms. So a V-enriched category has a set of objects as usual, and then between any 2 objects, there's a Hom object instead of a Hom set. And then instead of a composition function, I have a composition morphism in V, where this is the product in V. And then it satisfies analogs of the usual axioms of associativity and identities. The most famous, examples in enriched categories abound. They occur whenever we notice that there's additional structure on the Hom sets in some category that we're studying. So the most famous examples are additive categories, such as the category of vector spaces. I can add 2 morphisms between vector spaces. Or topologically enriched categories, where, for example, if I have 2 maps between topological spaces, I can talk about them being close to each other or deforming one into the other, which is using the topological structure on the Hom space. So a 2 category is nothing but a category enriched in cat, which is the 1 category of categories. So I start with the 1 category of categories. It's a category of finite products, and therefore I have a notion of category enriched in it. The main example is cat, the 2 category of categories. So the objects are categories, smaller categories. And for any 2 categories, I should define a Hom category. And for this, I take the usual functor category, the category of functors from X to Y, which has as objects functors and as morphisms natural transformations. There's a little star here because I wasn't being quite honest here, but in a way which is completely irrelevant for the talk. But if you are interested, you can ask me about it. Okay, you can also say what a 2 category is more directly without reference to the general theory of enriched categories. A 2 category has objects. We said that already. Morphisms, those are the objects in the Hom categories. And 2 cells, those are the morphisms in the Hom categories. Moreover, you can compose morphisms, as usual. You can also compose 2 cells. So if I have two cells sitting next to each other horizontally in this way, you can compose them and get a 2 cell of this shape. And you can also vertically compose two cells. This is actually, in a sense, a simpler operation. This is just the composition in the Hom category. If I have two cells sitting on top of each other, I can compose them to get a two-cell of this shape. And then there are laws. There are various laws. If you sort of unwrap the enriched category definition of two category, then you get all this structure, and then you get a bunch of laws. Associativity for a horizontal composition, for a vertical composition, and various other things. But it's a kind of simple equational theory with these operations and then a bunch of equations satisfied by them. Now, two-category theory is also a big subject, a very beautiful and rich theory, which I don't have time to go into. But one thing to say about it is that there are lots of examples of two categories. So whenever you have some collection of categories, like categories with finite limits, or abelian categories, or topoi, or whatever, the collection of all of them forms a two-category, and you can ask what properties that two-category has. And there are other examples coming from geometry. The theories of orbifolds and stacks like that also give rise to two categories. But more fundamentally, the importance of two categories comes from the fact that they allow us to express more categorical notions than are available in the one category of categories. Because we have access not only to objects and functors, but also to the natural transformations. So any categorical concepts which are defined using natural transformations can be expressed in two categorical language. For example, in two category of categories, we can talk about not only isomorphism of categories, but also equivalence, because that's defined using natural isomorphisms. We can also talk about adjunctions in an arbitrary two category, and things like that. As a general slogan, whenever you're considering the totality of categories and the relationship between them, the proper place to be operating is not the category of categories, but the two category things. Okay, so now I want to talk about trying to use two categories as a foundation for mathematics. So we begin in the same axiomatic manner as before, asking what the undefined notions would be in this theory. And an idea is, I take my primitive notions to be the sort of basic elements appearing in a two category. So now these are undefined notions. So like when I was talking about topos theory, I took set to be the primitive notion. But what I had in mind is that I'm looking at an object in a given category, topos. So here the primitive notions are category, functor, natural transformation, and then the three kinds of composition: horizontal, vertical, and composition of morphisms. Okay, so you could try to set out a axiomatic theory like this, and then the question would be, what are the right axioms? So to begin with, the axioms should include the laws of a two category, so associativity for the various kinds of compositions and things like that. But now, my interest is in having such a theory which can serve as a foundational theory of mathematics. So I should be able to express all the usual mathematical concepts and constructions. And for this purpose, I want in particular to be able to talk about the category of sets. So the point is, in the two category of categories, which is what we're trying to axiomatize here, there's a particular object of interest called the category of sets. And once we have access to the category of sets, then we can do set theory inside of that object, so to speak. And therefore, we have access to all the usual mathematics. So whatever this axiomatization of two categories is, of this foundational theory based on categories, functors, and natural transformations, it should somehow include the notion of a particular one of these categories, one of these basic objects of the theory, being the category of sets, or something like it.
And then you have access to objects by functors from a point into the category.
Absolutely, yeah. Any other questions about this before I proceed?
What's the Weber paper title?
This paper, it's called Ionative Structures from Two Topoi. Mm-hmm. And this is the paper, yeah, so you mentioned before the notion of cosmos, and this is very much sort of a development in that tradition. And yeah, this is the first paper that I know about where someone introduced the notion of elementary two topos. I mentioned Lawvere here also because Lawvere was really the originator of all this stuff. He introduced the notion of elementary topos and many of the notions of categorical logic. And he also introduced the notion of elementary theory of the category of categories. This, in fact, in his very first paper about topoi, which is called an elementary theory of the category of sets, he mentioned already at the end of that paper that something like a satisfactory foundation should be based on the category of categories. And then he wrote another paper called The Category of Categories as the Foundation of Mathematics. So that's very much a precursor to what I'm talking about today, except he was talking about the one category of categories, where from the modern point of view, I'd say it's rather clear that the proper object is the two category of categories. I also mentioned Makkai here, who in the 90s began working on a general foundational program based on higher category theory. And there are many aspects to his work related to this and various interesting ramifications. But the spirit of what I'm doing is very much part of his program. And in fact, he was the one who told me about these things and set me to work on this project. Okay, so now there's this mysterious word, the DOF classifier. So I want to tell you about what is the special axiom for a two-topos that lets us access something like the category of sets. And the fundamental idea, which is in Weber's paper, and which he attributes to Lawvere, and in a certain way is something extremely familiar from different parts of category theory and higher category theory, is that there's an analogy of this kind, that the object of truth values is to the category of sets as the category of sets is to the two category of categories. So to spell that out a bit, let's recall what omega was. It classifies subobjects. So Homs from X into omega are in bijection with the subobjects of X. And now we ask, what does set classify? What's the universal property of set regarded as an object of the two category of categories? And the answer is something called discrete op vibrations, DOFs. So the category of functors from an arbitrary category X into the category of sets is equivalent to the category of dots over X, which I'll say what that is. I'll say something about what it is in a moment. There's an asterisk here indicating that I'm also not being quite honest, and in fact in quite a crucial way. So there's something important I'm omitting here, which maybe I'll get back to. Okay, let me say what a DOF is, a discrete op vibration. So if you have a functor between two categories E and B, it's a DOF if it satisfies the following property. So I have my functor P from E to B, and the property is this: given the red things, given a morphism in the category B from X to Y, and given an object X tilde lying over X, which is to say P sends it to X, then there exists a unique lift F tilde of F. That's it. That's the property of being a DOF. Now, given such a functor, suppose I fix a morphism F in the base here, then I get this map F star from the fiber over X to the fiber over Y. That is from all the objects lying over X to the objects lying over Y. How do I do it? Given an object over X, I take this lift F tilde, and I look at what its codomain is. That gives me an object over Y. So for every F in the base, I get a map from the fiber over X to the fiber over Y, and therefore I get a functor from B to set. It takes an object X to the fiber over X, and it takes a morphism F to this induced morphism I just talked about. So this is the way, this is the basic idea of the way that functors from B into set correspond to discrete op vibrations over B. And this may or may not look unfamiliar, but it's a very fundamental construction in category theory. This is nothing but what's called the category of elements. So if I start with a functor from B to set, if you've seen the category of elements construction, that's precisely what gives me this DOF B.
So where did you lie?
Oh, okay. The lie is that there's some set theoretic issues that I have to worry about the size of the
Right, it has to be set kappa, yeah.
So I may get back to that later. Okay, so what is a two-topos? I'm not going to tell you exactly what a two-topos is, and in fact I can't quite tell you because there is no, unlike topos theory, which is a well-established theory where everyone agrees what a topos is, there is no agreed upon final definition right now of what an elementary two-topos is. It's something which is still in development. The state of affairs, as I mentioned, is that Weber proposed some axioms for what an elementary two-topos is, although with the explicit acknowledgement that it was incomplete, that further axioms would have to be added to produce a satisfactory theory. And part of my work has been to introduce some such more axioms, following, as I mentioned, work of Makkai together with Bill Boshuk, who started thinking about these things, and then
I think Boshuk is also a student of Makkai.
exactly, yeah. Yeah. So they sort of never finished their work, and Makkai told me about it, and then I started working. Now, among the axioms, which Weber already has, the most important is the existence of this dot classifier S. So there's something extra which I'm brushing over here, which is that you can make sense of a DOF not only between actual functors, but in an arbitrary two category. So that makes sense to have if you're given an arbitrary morphism in a two category, which is kind of a formal functor, you can make easy sense of what it means for it to be a DOF. And therefore you can define this notion of a DOF classifier in an arbitrary two category. Now, an important thing about the axiom that Weber gives and my axioms that expand upon his is that there are still lots of examples. So it's really a meaningful theory. So the main examples are if you have any small category C, you can define a two category of functors from C into cat. That's always a two topos. So just like the category of presheaves is always a one topos. Now, sweeping some things under the rug, which I may say something about, I have the following theorem. Given any two topos, in my sense, so in the sense of the additional axioms which I have on top of Weber's, the DOF classifier S is always an internal one topos. So you can also make sense of what it means for an object in an arbitrary two category to internally be a topos. And one of the consequences of this is if this is the category that Emilio was pointing out, I can look at the category of Homs from the terminal object into S. It's a consequence that this is an actual category and that is a genuine elementary topos. Among the things I'm sweeping under the rug, I should mention that it's important that, as far as I know, this theorem doesn't follow on the basis of Weber's axioms alone. It's important to include the extra axioms, which I add, which in particular put extra conditions on the DOF classifier. So it's not enough that it just be a DOF classifier, it also has to satisfy some other very simple and natural conditions that maybe I can get back to later.
And that's set in cat. So
Thank you. Yeah, absolutely. In the canonical example of a two topos, which is the two category of categories, S is the category of sets, and they satisfy all extra conditions. So the slogan here is that in the intended manner, two topos theory subsumes topos theory.
And don't you normally want set points to set to be the classifier?
Yeah, so that's the kind of universal element. So whenever you have an object with a universal property, it always has this universal element. And in the case of a DOF classifier, it'll have a universal DOF, which is exactly the forgetful functor from the category of pointed sets. So that phenomenon will occur also in two topos.
I'm curious how sensitive this is to axiomatizations of the category of sets itself. That is, does it matter?
I mean, the axiomatization I have in mind is always just the ordinary topos axioms. So when I say this, or maybe I didn't understand the question. I mean,
the sets can have regularity or not. I suppose you get around this because the DOF classifier is just a one topos, right? So perhaps it doesn't matter. Yeah, I'm not sure what I mean by the question.
Yeah, it's an interesting. Yeah, I'm also not sure what you mean, but it does sound like an interesting question.
That is to say, you talk about the category of sets all the time, right? But sets have different axiomatizations. So
yeah, I see what you mean. So the properties that we can state about the category of sets will depend on what basic set theoretic assumptions I'm making in my background set theory. And the same is going to be true to a certain extent of two topos theory. But I'm
that is, I think there is a theorem here. I think there is a theorem here, some sort of independence or a conservation theorem that says that it doesn't really matter so much what the axioms of the category of sets are.
Oh, okay. That's a very interesting direction. Maybe we can return to it later at the end of the talk. I will say something in that direction about the relationship between for example, consistency of the axioms of set theory and the consistency of topos theory and things like that, of two topos theory. Thanks a lot for the question. So to repeat the slogan, when we operate in two-topos theory, in this axiomatic foundational theory, we have sort of one-topos theory embedded inside of it in this way. And therefore, we achieve our goal of being able to do ordinary mathematics to the extent that we can do it in ordinary topos theory. So the goal for the rest of the talk is to explain how two-topos theory not only subsumes topos theory, but also ordinary axiomatic set theory. So now I'm going to turn to talking about set theory. Any other questions before I do this? Okay, so first I'm going to make a distinction between two concepts called abstract and concrete sets. So when we're thinking of topos theory as a kind of set theory, it's important that the sets involved are abstract sets in the following sense. There are no things, entities in the theory such that I can take one of those entities and take one of the sets and ask, is this thing an element of this set? Rather, that's just not how the theory works. It's not built that way, right? I don't have this element relation between things and sets. Rather, I just have the sets themselves, the objects, and the mappings between them. Now, I can talk about elements of a set, as we've been talking about, maps morphisms from the terminal object. But in such a case, it's always that I first fix the set X and then look at a morphism from the terminal object to that set. It's not the case that I can just have an element by itself and then ask, is this element a member of this set? That doesn't make any sense, right? So that wasn't quite precise, but I hope you see what I mean. By contrast, in ordinary axiomatic set theory, we do have this element relation, and it's completely fundamental in the sense that it completely characterizes a set to say which things are an element of it, right? This is supposed to be a capital Y. Two sets are equal if and only if they have all the same elements. More specifically, the standard axiomatic set theories such as ZF deal with not just these concrete sets, which have elements, but more specifically, so-called pure or hereditary sets. That notion is that a set is pure if all its elements are pure. So it's a recursive notion. I figure out whether a set is pure by looking at all its elements and asking whether they're pure, which in turn I do by looking at their elements and asking if they're pure, and then it bottoms out at the empty set. So the base case of this recursion is that the empty set is pure, because vacuously all of its elements are pure. I'll say something more about pure sets in a moment, but it's really a familiar concept. And just before leaving the slide, I want to mention these names. Lawvere in 76 wrote a paper in which he talks about this notion of abstract set very explicitly and points out that topos theory is a theory of abstract sets. And Makkai expands further on the notion of abstract sets as part of his general higher categorical foundation program, and ties it quite interestingly to the the sort of philosophy of mathematics known as structuralism, which has close ties to category theory in general, and which was initiated in a famous paper by Ben Asaraf.
So abstract sets is a philosophical definition, not a mathematical one, right?
Right. I mean, yeah, absolutely. It's to begin with a philosophical one, although you can try to substantiate it by making some formal definitions and trying to prove something about it. That's part of what Makkai's work does. He has a theory called abstract set theory, and then there's a sort of meta theorem about it, which substantiates in some way the fact that the sets are isomorphism, are abstract, which is something like saying that any two sets which are isomorphic have to have all the same properties, which is not the case with concrete sets. But yeah, thank you for that clarification. You should regard this slide as being motivational or conceptual. Likewise, with the notion of pure sets, it's to begin with an intuitive definition. All of this you can actually quite easily make precise. I also just point out Cantor is here, of course, the inventor of set theory. Lawvere in this paper, or perhaps somewhere else, points out that Cantor actually also had this notion of abstract set as part of his general set theoretic conception. So it's quite a fundamental notion. But right now I want to talk about pure sets. So let's look at some examples of pure sets. So to begin with, the empty set is pure, as I said. And then since this set is already pure, if I form a set just containing that set, it's also pure by the recursive definition. So the set containing the empty set is pure. In general, all pure sets just look like a whole bunch of parentheses, possibly infinitely many. So now I have these two pure sets A and B, so if I form sets out of them, those are also pure. And now I have these four pure sets A, B, C, and D, so these are all pure, and so on. I can keep going like this. So the pure sets come in these stages. At each stage, we form pure sets by assembling sets out of the sets occurring in previous stages. And these stages are very famous and have a name. They're collectively called the cumulative hierarchy or the von Neumann hierarchy. And the alpha stage of this hierarchy is usually denoted V alpha. Maybe for von Neumann, I'm not sure. The union over all the alpha is therefore the totality of all pure sets whatsoever. So again, I regard these first of all as just naive, intuitive set theoretic notions, but it's possible and quite easy to make all this precise within the context of axiomatic set theory.
Yeah, because sometimes what they do is you start off with first order logic formulas, and you call those like classes, right? And then you have like x equals x is like the class, and like you try and prove that something belongs, so that you call that a set. But this is this I don't know. I don't have a precise question, but I'm trying to figure out where this sits in that formalism.
Yeah. Maybe we can discuss it more later, but I'll just say that it is a theorem, for example, of ZF, that every set, for every set X, there exists an alpha such that X is an element of V alpha. So it's really a theorem in the theory that the cumulative hierarchy exhausts the whole universe of sets.
So even with what I said, everything in.
Yeah, so in terms of what you said, that you were talking about the class of all sets, X equals X, ZF says that class is coextensive with V.
Doesn't V go back to Gödel?
No, so Gödel's famous for introducing L, the
opposite of V.
The universe of constructible sets, which is a subclass of V. And then one sometimes contemplates the axiom L equals V, which is to say every set is constructible. That's what Gödel used to prove the.
What did you say? Coextensive with?
I just mean they have all the same elements.
Oh.
Okay, so that's the notion of pure set. I hope it's clear. Okay, and now here comes the sort of fundamental and by now quite old idea which connects pure set theory with abstract set theory. And it's that pure sets can be regarded as abstract structures in the following way. So first, preliminary definition, we call a pure set transitive if it contains all the elements of its elements. So X is a pure set. Suppose Y is contained in it, therefore it's also a pure set by definition. And then Z is contained in Y, then Z should be contained in X. Okay, that's what transitive means. And I hope that it's obvious why we call it transitive. The transitive closure of a pure set is the least pure set containing X. Maybe this should say the transitive closure of the singleton X, but I won't worry about that. So an example, look at this crazy pure set. If I want to find the transitive closure, I have to adjoin to this set all of the elements of its elements, and so on. So this set contains this bracket empty set. So its transitive closure still contains that. But then bracket empty set is an element of that, and therefore it also has to contain that. And then empty set is an element of that, so it also has to contain that. So that's what the transitive closure looks like. So it's sort of, I join all the elements of elements forever. Now, we start with a pure set, we form its transitive closure, and we equip it with this simple binary relation. So the transitive closure is a set of pure sets, all the elements are sets, and so we say Z is less than Y if Z is an element of Y. Okay, and now here's the first fundamental fact. Given two pure sets X and Y, I form their transitive closures and equip them with these binary relations. If X is equal to Y, obviously these structures will be isomorphic, they'll be equal in fact. But conversely, If these are isomorphic as abstract sets equipped with a binary relation, then X is equal to Y. So what's the idea here? The transitive closure of X remembers the entire history of how it was built up in the cumulative hierarchy, right? All the way from the first stage, it contains all the things which eventually go into the constitution of X. And this membership relation remembers which of those things are elements of which one, and therefore altogether they suffice to completely reconstruct the set X. That's the intuition behind this theorem. So the old theorem of Voevodsky, an early logician and set theorist, well, maybe not that early, and Kolanosius sort of rediscovered or reproved this theorem in the present context of relating topos theory with set theory. So expanding, the full thing that Voevodsky proved is this. Suppose we have a general set X with a binary relation, and we're wondering whether it is of this form. Is it isomorphic to the transitive closure of some set, some pure set with the membership relation, which is then necessarily unique by the previous thing? And the answer is yes. Oh, this missing period here. The answer is yes if it satisfies these three conditions. So I don't want to spend too much time on the conditions, but I'll just quickly go through them. So first of all, the relation should be extensional in this sense, which is an analog of the axiom of extensionality. So two elements are equal if and only if they have all the same predecessors. It should be well-founded, or also known as Noetherian in the usual sense. Any non-empty subset has to have a minimal element with respect to this relation. And finally, it has to have a maximal or top element. So any downwards closed set containing that element has to be the whole thing. In other words, it has to have some element such that if I look at the set consisting of it, all its predecessors, all their predecessors, and so on, I get the whole set. So these are three properties that I can impose on some binary relation. And the precise details aren't important. The important thing is there are some conditions, some very easy to state conditions that I can put on a binary relation which force it to be of the form transitive closure of a set. Let's call a structure X less than, satisfying these three properties, a Voevodsky structure. In deference to this lemma. What is the upshot of all this? I have this map from the universe of pure sets to the class of Voevodsky structures, or isomorphism class of Voevodsky structures. This thing is an isomorphism. Or, okay, first of all, I want to say it's a bijection, but I claim there are some extra structure on both sides, which are also observed. But mainly it's a bijection. So it's injective by the first thing I said. If two pure sets have the same Voevodsky structures, then they're equal. And it's surjective by the second thing I said. Any Voevodsky structure is isomorphic to a pure set. Slogan: this construction subsumes pure set theory into abstract set theory. From this perspective, pure set theory is the study of certain abstract set theoretic structures, namely Voevodsky structures. So I don't have to worry about sort of pure sets as a fundamental notion. I just start with abstract sets. On my abstract sets, I consider these binary relations satisfying these properties, and from that I can recover the whole theory of pure sets in this one. Okay, because I can talk about pure sets now in the context of abstract set theory, I can do it in topos theory. So a Voevodsky structure in a topos is simply an object, a binary relation, and it should satisfy the three axioms I gave in the lemma. And now, how do I make sense of these three axioms in a topos? Well, I know how to interpret arbitrary logical formulas in a topos. So I know what it means for an object and a binary relation in a topos to satisfy these properties. So that's what we call a Voevodsky structure in a topos. On the basis of this, we can interpret pure set theory into topos theory. What do I mean here by an interpretation? For each of the primitive terms in pure set theory, I should interpret them as some concept defined in the topos theory. So in particular, when I say set in pure set theory, I want to interpret that as meaning a Voevodsky structure in the sense of topos theory. So in the axiomatic topos theory set, I can define a Voevodsky structure. It's just a set with a binary relation satisfying those axioms. And therefore, I can interpret set to mean Voevodsky structure. For this to be a good interpretation, this interpretation of the primitive notions of pure set theory should satisfy all the axioms. So when I interpret set as Voevodsky structure in a topos, I also have to say how I interpret the element relation, which I haven't told you anything about. It should satisfy all the axioms of ordinary pure set theory. And the answer is it doesn't quite. But this now classic theorem of Cole-Osius that I told you about, Osius, is that if I put certain additional assumptions on the topos C, so it's not just a pure topos, it's a topos together with some additional assumptions, then the resulting interpretation doesn't satisfy all of ZF, but some fragment of ZF. Okay, so the theory of Mostovsky structures in a topos gives me some interpretation of some weak form of ZF set theory.
But it's only the transitive sets, right?
No, yeah, that's confusing. But remember, I started with an arbitrary pure set and then took its transitive closure. So the Mostovsky structure itself sort of encodes a transitive set, but that transitive set came from the transitive closure of an arbitrary set. You see what I mean? So up here, that's a very good question. This map, this bijection is a map from all class of all pure sets. Yeah, thanks a lot.
So that partially answers my question, partially.
Great. Okay. And yeah, I'll say a little more about it. Yeah, thank you.
Yeah. Now, is that set, that object, a representable, the representing element for the discrete vibration?
Well, certainly not in their version, but in my version of this theorem, which I'm about to state, it's very much that kind of thing.
Yeah. Okay.
Okay, I'll mention. So this was in 72, sort of near the beginning of topos theory. Since then, there's been a lot of elaborations and variants of this kind of work. And I'll mention a significant one, which is this work of Joel and Moerdijk. They wrote a book called Algebraic Set Theory in 1995. And they used a different construction to produce a model of full ZF. The asterisk here is, again, that I always mean intuitionistic ZF and not with classical logic. So they take a topos C and get an interpretation of full intuitionistic ZF in C. Again, after putting additional assumptions on C, which they call it being a category of classes. So this is very interesting, and I would love to say more about it, perhaps later. But I'll just say now that the basic idea is that you take C to be something not like the category of sets, but the category of classes. In particular, there's a specified subcategory, which is like the small objects. So you have this large category of classes, and then within it, a smaller category of sets. So that's sort of the basis for their construction, and their construction is quite different from this other one using Mostovsky structures. I also just mentioned as a reference, there's this website. If you just Google algebraic set theory, you get to it. It's a little sort of compendium of all the different work that's been done on algebraic set theory since then, which is And I also mentioned in particular Schulman's paper Stack Semantics from 2010, which is among other things, it does many interesting things, but in particular tries to sort of synthesize these different approaches to category theoretic constructions and models of set theory. So, in conclusion, I'll mention my theorem from a paper that I hope will come out soon. Here it is. Start with any two topos, and you construct a model of full ZF set theory, full in the same sense as before, intuitionistic set theory. And the proof combines elements of both of the above constructions. So it I somehow create this theory of Mostovsky structures internally in the two topos. And then I also create something like a category of classes internally in the two topos. And I'll also mention that as I was kind of just mentioning, this approach of combining these two methods is also very closely related to what Schulman does in that paper and in other of his writings. Yeah, so that's basically as far as I wanted to get. I'm already a little over an hour. I have some bonus slides that I could get into if there's interest. But I'll stop here and ask for questions or discussion. And if we want, we can look into the bonus slides. So thank you very much for your attention.
How many bonus slides do you have?
There are 4, but they're all kind of chunky.
Yes.
Bonus. Okay.
Okay.
Okay, should I go ahead with the one, or
In
does
your
anyone want to?
Yeah, let's
in
go
your
on.
in your abstract talk, you did mention size issue, and I see you have a
Yes.
slide on that. So maybe just two words on what, a word or two on what that was in the app.
Okay, thanks for the question. Yeah, so size issues. So as I mentioned with an asterisk before, and Emilio asked me about, it's not actually quite true what I said. It's not the case that the category of functors from a given category X into set is equivalent to the category of DOFs over X. It's rather, on the right side, I have to put the fiber-wise small DOFs. If we look way back at the construction I explained, where you go between a DOF and a set-valued functor, starting with the DOF, I get the functor from B to set by sending each element to its fiber. But therefore, those fibers should be sets and not classes. They should be small discrete categories. So that makes it a little bit more complicated. On the right side, I have to put the fiber-wise small DOFs. In particular, in a two topos, it's no good to demand that this S has the naive universal property of the DOF classifier, that there's an equivalence between HOMs from X into S and the category of DOFs over X. Rather, it's only reasonable to demand that it be fully faithful, right? This thing is really a full subcategory of this one. The fiber-wise small DOFs are a subcategory, full subcategory of all DOFs. So Weber's axiom about the DOF classifier is really, first of all, that you have this canonical functor and it's fully faithful. And it's the main point of the axioms the extra axioms that I introduce following Makkai and Boshuk is to put additional conditions on this S, because it's really very weak just to demand this is fully faithful. For example, if S is the empty category in two categories, it satisfies its universal property. Like this is fully faithful because the left-hand side is just empty. So anyway, so that's some of the important subtleties that come into this theory. And the sort of starting point of this project, as Makkai originally advertised it to me, is to ask the question, what if I do demand that this is always an equivalence? That's something like saying every class is a set. Every class is small, right? That if, for example, if I take X to be the terminal category, then cat X to set is just the category of sets, and DOFs over X is just the category of classes, of possibly large categories. So this would be saying every class is a set, and that's the kind of thing that gets you into trouble. That gets you things like Russell's paradox. So this is the theorem that if a two topos does contain a DOF classifier, such that this is really an equivalence, then C is trivial. And the proof goes by, so this was the paradoxes from the title.
But you don't like introduce Grothendieck universes into these two toposes in any way?
That's a good question. In a sense, yes, but the point is that each DOF classifier S serves as a Grothendieck universe. There's not a prior notion of Grothendieck. So if I had a prior notion of Grothendieck universe, then I would want to demand that S be the eternal category that's in that universe.
Yeah, you would want one for every kappa, and then you would want that to be an equivalence for DOF kappa.
Exactly.
Yeah.
But so it's rather each DOF classifier S gives me a kappa. It gives me a notion of small set, namely small with respect to S.
Mm-hmm.
Okay. Any other questions?
You were going to say more about the paradox. Oh, yeah.
Igor, talk.
Thank you. So you mentioned several times Lawvere's theory and Cantor. So Lawvere developed a theory of axiomatic cohesion as a categorical foundation of Cantor's work on set theory. So within that theory, he has a notion of a cohesive or pre-cohesive topos, and basically it is defined by a string of junctions between two topoi. One is a topos of spaces, so which some sort of cohesion, and the other one is a topos of sets. So my question is, since you are working in the context of two categories, did you ever try to characterize the category of sets or pure sets or whatever? There's also a version of the model of the category of sets by means of decidable objects in topoi, which roughly correspond to decidable sets in computation theory. But my question is, did you ever try to derive some sort of characterization of set theory by means of two adjunctions? Because in a similar way how Lawvere did it at a one-dimensional level, because your basic setup is a two category of categories.
Okay, that's a very interesting question. So, I mean, I kind of heard two questions in there. One is, and maybe this wasn't actually the one you're asking, but I would like to answer it anyway. The something which I've been very interested in working on, but haven't done yet, since I'm still writing this up, is to do topos theory inside of a two topos. That's a very reasonable thing to think about. For example, what you were just talking about, having a cohesive topos, which is a topos living over the category of sets. If I'm inside of a two topos, I have my dot classifier S, and I can consider internal topoi living over S. And then I could try to sort of internally reproduce the theory of cohesive topoi, or more generally, the theory of topoi over a given base, which I think is a very promising avenue that I would like to pursue, or that I'd like someone to pursue. The other thing I heard you asking about, which I haven't thought at all about, is this a kind of categorification of the kind of thing Lawvere was doing, where I fix a base two topos like cat, and then look at other two topoi living over cat. And that's also extremely natural thing to do, but yeah, I haven't really thought at all about that question of looking at different two topoi and geometric morphisms between them and things like that. But it's a very natural question.
Okay. I mean, the additional question would be, there's a well-known string of adjunctions, four adjunctions between cat and set, starting with connected components and so on, discrete, object functor, and condiscrete.
Okay.
So maybe that could be also a context to express.
Yeah, I mean, sure. Right. Yeah, so maybe I'll say something about that in the context of another one of the bonus slides. Namely, in a two topos, you might well want to internally construct the one category of categories. That's what you were just making reference to. And in general, the nice thing about two topos theory is I not only have set, so that's the way I've been talking about it. I have this two category, and then I zoom in on this particular object, and then I do topos theory inside of there. But if I live my whole life inside of there, I'm not taking advantage of the fact that I have this whole ambient two category. So it's nice to know that we can also define other categories of interest as objects in my two topos. The category of abelian groups, the category of topological spaces, what have you. Or in general, as in this example, the category of small one categories. So here's a construction in that spirit. So this is a two categorical generality. Given any object x in a two category C, I can say what I mean by an arrow object of x. So in the two category of categories, this would be simply the arrow object of it, the arrow category of x, the functor category from category consisting of a single arrow into x. And it has this obvious universal property that the on category from A into the arrow category is the category of arrows in the Hom category. So it's easy to see that the real arrow category in the two categories satisfies this property. And as usual, being a universal property, it determines x arrow up to equivalence. Here's a generalization of that, where I replace the arrow with an arbitrary small category j. I really want to think of j as being finite. So given an object in a two category and a small category j, the cotensor of x by, this is a typo, it should say x by j, is determined by this universal property. So the same thing, where I just replace the arrow by J. Here's a general two-categorical fact. This is a very famous fact that goes back to Kelly's original manuscript on enriched category theory, and it's something in the spirit of pullbacks and terminal object or products and equalizers generating all finite limits. In a two-category, if you have finite limits in the usual one-categorical sense, and you have arrow objects, then you have all cotensors by finite categories. So that's a very pleasant thing, that in any two-category with finite limits and arrow objects, you can make sense internally of the object of functors from J into X internally. And so this, if I take X, for example, to be my dot classifier S, which is supposed to be serving as the category of sets, then this is a category of structures of a certain kind in X, right? For example, this example would be just the category of maps, which is that's a basic kind of set-theoretic structure. Here I get some more elaborate things. And the point is, I'm on my way to being able to talk about more complicated structures. I want to talk about something like the category of rings in X or groups in X. This is already some category of structured sets in X.
So
and one of the
if X on the first line is an internal topos, then X to the power is like internal Sierpinski topos, if I understand correctly.
Exactly. Yeah, that would be an example. Yeah, exactly. This would be the Sierpinski topos. And so here's a theorem I prove. So it's a very general theorem. In fact, not just second order theory, but higher order theory. So I consider a general second order theory. So I have a set of sentences concerning the elements of a set X, given functions relation on X, and subsets of X. So this could be a great variety of things. The theory of groups is actually a first order theory. The theory of rings or monoids or whatever it is. Also, the theory of Mostovsky structures is a second order theory. In fact, we saw above exactly what there are three sentences saying what it means for a given set with a binary relation to be a Mostovsky structure. Now, given any finite second order theory T, you can talk about the groupoid of all models of T in C and isomorphisms between them. So I already mentioned that we can talk about Mostovsky structures in a arbitrary topos, and you can also talk about isomorphisms of Mostovsky structures, therefore you get a groupoid. And here's one of the theorems in my paper that whenever you have a Dopf classifier S, it admits a cotensor by any finite second order theory. But this is supposed to be a cursive T, so it satisfies this condition that, okay, this doesn't determine it completely. I have to put something more general on the left-hand side. But in particular, this is a consequence that the category of global elements, so the Hom category from 1 into this internal object of models of T, is the category of models of T in this topos. So on the basis of this, okay, there's a catch here, which is that I'm saying groupoid rather than category, but a similar construction gives you categories in appropriate circumstances. This construction really allows you to define the object of models in S of any theory you want, basically. So now in my two topos, I can talk about the category of groups, the category of abelian groups, the category of the algebras, and so on, using this construction. And okay, now I've almost got through the bonus slide, so I might as well just finish it off. So so this construction allows me to talk about the internal object of Mostovsky structures. So starting with a real external topos, I can form the groupoid of Mostovsky structures. But now also, given my internal topos, this dot classifier, I can also talk about the object of Mostovsky structures in S. And you can prove that this object is discrete. This amounts to the fact, an interesting fact, that if you have any two real Mostovsky structures based on sets, if they're isomorphic, there's a unique isomorphism between them. So they're kind of rigid. Or in other words, a Mostovsky structure has no non-trivial automorphisms. So this internal universe of Mostovsky structures is discrete. which is to say that the morphism to the terminal object is a DOF. Now, any DOF is classified by the DOF classifier. That is, if we make this too strong assumption that I said leads to a contradiction, that our DOF classifier S classifies all DOFs. In that case, this discrete object, the universe of Voevodsky structures, would itself be classified by some map into S. So, okay, I know this is all a little much, but I just want to give you a flavor of it. The conclusion is something like the universe of all sets, this Voevodsky class of Voevodsky universe of Voevodsky structures is something like the universe of pure sets. And in this case, we get that the universe of sets is itself an object in the category of sets. And that's a problem. That's starting from there, you get to this Russell-type contradiction and conclude that the two category is trivial. So instead of making this too strong assumption that S classifies all DOFs, what we do is assume the existence of a second DOF classifier, S prime. This is something like Grothendieck's famous axiom of universes, which says that for any set, there's a universe which contains that set. So I have this discrete object, M of S. I'm not going to assume that it's classified by S itself, but I assume there's some bigger universe S prime is classified. The result is that I get this M of S as an object of this topos of S prime small objects. And this topos has an interesting structure. It has a special subtopos consisting of the S small objects. So this is very much like one of the categories of classes of Joyal-Murdoch. I'm looking at this category of S prime small discrete objects. Those are like the classes. Within it, I have the S small discrete objects. Those are like the sets. And within this category of classes, this object of Voevodsky structures has a special property, a universal property, which determines it up to isomorphism. It classifies the S small Voevodsky structures. And then the thing that I prove is that so I sort of axiomatize this situation in general, some category of classes type situation, and then a special object in it, which classifies the S small Voevodsky structures. And the theorem is that any such object is a model of ZF. So that's how I prove the theorem that that any two topos contains a model of ZF. And this is also a somewhat more precise statement of what that actually says.
Nice. Any question? Well, thank you again. That's a bonus clap. Any questions?
Okay, I have a question. So, you didn't tell us the full definition of two topos yet,
Yeah.
right? But it is a kind of two category.
Yep.
So are you positing a background set theory for that, or are you using an axiomatic thing?
Good question. Importantly, it's an elementary theory. It's a first order theory. So you don't need any background set theory to talk about it. And that in the same way, so it has the same status as ZF, the ordinary axiomatic set theory, and of topos theory. And in all such cases, there's sort of two perspectives you can take on it. You can take topos theory as a completely sort of fundamental notion. In fact, McLean at the very beginning of categories for the working mathematician also uses this device. He introduces something called a meta category. It's very much in the same spirit of that. When I talk about topos theory, I can, like I say, take those as undefined notions. I have this thing called an object and this thing called a function and so on. Or I can, it's basically equivalent, but I can forget about that and just put myself in the ordinary mathematical situation of having an ambient naive set theory and just talk about a topos as a mathematical object. It's a category satisfying certain assumptions. And so with two topos theory, it's very much the same thing. A two topos is a two category satisfying certain assumptions, but those assumptions are all elementary. So to illustrate what I mean by that, when you talk about a Grothendieck topos, for instance, you have to say that it's complete or co-complete. When you're talking about the axiomatic approach to Grothendieck topoi using Giraud's axioms, the completeness or co-completeness is non-elementary because you need a prior notion of set to say what you mean by complete or co-complete under small limits. By contrast, the axioms of an elementary topos are all elementary in that it's simply you have these basic objects and operations and relations, and you're stating some first order properties of them.
Right, because it's all finite limits, so that can always be written as a finite term.
Yeah, exactly.
Yeah, I see.
So two-Dobos theory is very much the same kind of thing, and it's important that it's like that. That's, in my eyes, that's what it gives it a legitimate status as a foundational theory. Thanks for the question.
So, sorry, my question is actually on sort of your last two lines, where if it's an S small most key structure, any model for ZF and C, that means that it comes up with the same set theoretic paradoxes as if it's small. Is that correct?
Oh, right. Okay, maybe I understand your question. That the like, yeah, I could put myself in this situation that I have this like category of classes pet situation, and then I suppose that I have an object classifying not only the small Mostowski structures, but all Mostowski structures. Then I get the paradox.
Okay.
Any more questions out there? Lots of people today. It's a wonderful talk. If not, so let's thank our speaker again. And the semester's over, and we'll be back next year, hopefully next semester. And thank you all for listening. Are you gonna send me your slides?
Sure.
So I'm gonna post the slides so it's easy to get. Okay, ladies and gentlemen, thank you very much. Have a wonderful day, wherever you are.